All right, just a couple things about domain and range notation. So in the last example, I talked a little bit about brackets. You know, if you wanted to say that x was taking on values greater than 0 but less than or equal to 7, we would use a parenthesis 0, comma, 7 bracket. There are a couple of other notations you can use for things like what if it's the entire set of real numbers? Well, you can use this funky R looking thing, or you can say negative infinity to infinity. Now we use parentheses on this because again those are non-attainable values. In fact, it's not even a number, it's a quantity, so you would have to leave them as open. Do not close anything that involves infinity. The other thing that we can consider when using domain and range is how we link things together. So one of the problems that we looked at before had something like x was greater than or equal to 0, and then x was greater than 2, less than or equal to 4. So if we take that and we want to write it as a single interval notation type of problem, what we would say would be, all right, so the first piece would be considered negative infinity up to 0, and the second piece would be considered 2 to 4. And rather than using a conjunction like and, we would take and use the union symbol, so kind of like a giant U, to represent everything between negative infinity and 0 in union with everything from 2 to 4. And even, you know, some people wanted to use this type of notation, like real numbers minus x equals 2. Well, real numbers minus x equals 2 is not good math notation at all. If you want to talk about all the real numbers but not the number 2, you would say take all of the numbers from negative infinity to 2 and unite that with all of the numbers from 2 to infinity. And as long as you're using parentheses and excluding the 2, this is every number from negative infinity to infinity, not including the 2. So this would be a much better notation to use, and the notation that would be expected on the AP exam. Speaking of domain and range, there were two problems that people tripped over on number 9, and that was 9C and 9D. And I think that we'll take C first. When looking at the square root of 4 minus x squared, we know that whenever we deal with these radical expressions, we have to be careful about throwing negative numbers underneath. So one way to start dealing with this problem in terms of its domain is consider where 4 minus x squared is equal to 0. And if we can identify where it's equal to 0, we can generally identify where it's positive and where it's negative. So if you solve this, you get x squared equals 4, x equals plus or minus 2. So plus or minus 2 are the points that make this equal to 0, and you can take the square root of 0. That's not an issue. If you treat this the same way we were talking before, that's breaking this into the region negative infinity to negative 2, negative 2 to 2, 2 to infinity. Okay, these are the intervals that we have to consider. Which ones are problematic? They will not be in the domain. So just choose some values like negative 3. If you do 4 minus negative 3 squared, you get 4 minus 9, which is negative. You cannot take the square root of that. That is not in the domain. If you take a number like 0 and plug it in, 4 minus 0 squared is 4. Take the square root of 4, it's 2. This interval is in the domain. If you take a number like 4, 4 minus 4 squared is 4 minus 16 is negative 12. Can't take the square root of negative 12. So we know that the domain for C, so the domain for letter C is going to be the open interval negative 2 to 2. Now to get the range for that, inclusive, negative 2 to 2 inclusive, because it can equal 0. To get the range for that, you can start plugging in values, but there's infinitely many of them. So maybe consider something like this. What does the graph of 4 minus x squared look like? Well, the graph of 4 minus x squared looks like this. It's a parabola. Shifted up 4 and it's inverted. We're only taking the square root of these values. In doing so, we know that it's going to take the square root of the positive and negative values for x the same way because y is positive there, it just won't go below here and it won't go below here. So essentially, just using some understanding of the graph of 4 minus x squared, I have a decent idea as to what the square root of 4 minus x squared looks like. It actually looks a little bit more semicircular. Looks a little bit more like that. But, who's judging at this point? The point being is it's clearly got a maximum value at x equals 0. So at x equals 0, I would have 4 minus 0 squared, which is 4. Square root of 4 is 2. So in terms of the range, I would take and say, okay, I know that 2 is going to be the largest value. The smallest values are occurring when the function actually hits the x-axis. And we know that that's occurring when x is equal to 2 or negative 2. When it does that, if you plug a 2 or a negative 2 in, you're taking the square root of 0. So our range is from 2 to 0 inclusive. You can use the same type of argument for the square root of x squared plus 4. When you take the square root of x squared plus 4, now you have an upward opening parabola. Taking the square root of it, again, makes it a little bit more semicircular, but it's going to continue up. There's no restriction on that. So for D, when we're talking about the domain of D is not restricted. The square root of x squared plus 4, there are no values that I can plug in for x that make this undefined. So I would say that it's all real numbers, or if you want to give a negative infinity to positive infinity, open interval, that would be its domain. Its range, again, clearly takes on its smallest value when x is equal to 0. So that's going to be 2. And it goes off to infinity. It's not bounded above. So that would be your domain and range for 9C and 9D. I think I talked about even and odd enough in class the other day, but I still wanted to go over these two problems. So again, even, odd, or neither. So we have a couple of cases that we consider. They both deal with f of the opposite of x. So if f of the opposite of x is equal to the opposite of f of x, we say that the function is odd. If the negative sign gets absorbed, so if f of the opposite of x is just equal to f of x, we call it even. And if you're neither not odd nor even, then you're neither. So not all functions are considered odd or even. There are many, many functions that are neither. In fact, infinitely many. So all we have to do is say, what is f of the opposite of x? So if I plug in the opposite of x into each location of x in the function, and then evaluate and simplify. So the opposite of x cubed is the opposite of x cubed, and plus a negative x is just a minus x. I can then factor out a negative, and I'm left with x cubed plus x, which was my original f of x value. So I've actually shown generically that f of the opposite of x is equal to the opposite of f of x. Therefore, this be odd. B ends up being even, because if I take f of the opposite of x, it's the opposite of x squared plus 1. When you square a negative, you always get a positive back, so the opposite of x squared is just x squared plus 1, which is f of x. So f of negative x is equal to f of x, therefore even. All right? If you had like x squared plus x squared plus x is neither odd nor even. That would be a good example of one of those. 14b, oh, excuse me, hiccup. 14b was one that a lot of people dropped the ball on, and just wanted to talk about it. So it seemed like most people understood how to find an inverse. So set f of x equal to y, and then swap your values. Call that an x, call this a y, and now resolve for y. So 2y squared is x minus 5. Y squared is equal to x minus 5 over 2. And then here was where the ball dropping came in. Y is equal to plus or minus the square root of x minus 5 over 2. So pretty much if you have a plus or minus in your answer, it's not a function. If you consider the graph of any square root function, it's even easier to see graphically that let's see here, when x is 5, this whole thing is 0. Here is the positive square root of x minus 5 over 2. Here's the negative square root of x minus 5 over 2. And there is the failure of the vertical line test, so no, it is not a function. All right, the non-calculus approach to this particular problem. The first thing that needs to be said is that you have 240 feet. You have x and x on either side of your rectangle, so this question mark here is just 240 minus 2x. That's how much fence you have for that side. And the question is about the area. So if I want to write an area equation, so a of x, it's simply the product of the length and the width. So it's going to be x times 240 minus 2x, or negative 2x squared plus 240x. A nice quadratic. We want to find the values for which negative 2x squared plus 240x equals 5,500. And it was summer and there wasn't much of a restriction, so I don't know if you actually tried to solve this on your calculator. You could do so. Or you could set up this as a quadratic. I'm going to do it right over here. Negative 2x squared plus 240x minus 5,500. And then set that equal to 0. And use the quadratic formula. You have an a value, you have a b value, you have a c value. Using the quadratic formula, you will get two values of x for which this is true. The first one, let's see here, it's like 60 plus or minus the square root of 34 or something. I have to find this in my notes. 5 radical 34, which is approximately 30.9 or 89.2. Either one of those will work. So just use the quadratic formula to get that answer. For the maximum, again, going back to this negative 2x squared plus 240x, this is a parabola. So graphically, if you think about it, looks something like this. Takes on an area of 0 if x is 0 and then gets bigger and then eventually gets smaller. You're really just being asked to find, for what value of x does the maximum occur and then evaluate for that. To do so, the vertex of this parabola occurs at the opposite of b over 2a, or 60. And I have an area function above, so if I can find a of 60, which would be 60 times 120, this would be the maximum area. So a of 60 is equal to 7,200 square feet. So that's how you would go about doing problem number, whatever that is, 15. Yep, 15. All right, last one I want to talk about is maybe cleared up by what we did in class, but again, a lot of people miss this one, and it also does tie into the notation. So that is, on what interval is the function continuous? So this function is discontinuous, and we can see that by looking at what happens when we take f of 2. And the function is defined as 5 minus x when x is equal to 2, so f of 2 is equal to 3. If you look at the limit as x approaches 2 from the left, and the limit as x approaches 2 from the right of f of x, we'll see that as you're coming in from the left, we're still on the 5 minus x piece, so the limit is equal to 3. If you're coming on the right, though, greater than 2, you're on this piece, you're at 4 minus 3, or 1. So therefore, the limit does not exist, which means that we have a point of discontinuity at, that's a horrible at sign, I'll draw that again, at x equals 2. So the function is discontinuous at x equals 2. However, 5 minus x and 2x minus 3 are both continuous functions. They're nice linear pieces. So if I want to tell you where the function is continuous, I will just say everywhere except for x equals 2. So negative infinity to 2, union 2 to infinity. And that would be the intervals of continuity for this particular function. All right, well, hope that was enjoyable. I'm losing my voice for talking so much. I will see you tomorrow.